Oh, you just have to like the one on the top one, right? The arrow, right next to save.
Okay.
Hello everyone, this is Jahangir Alam. I'm going to present today our work titled how to compare situation in which we measure different quantities with different uncertainty. So in this project, there are my collaborators, other collaborators, were Ismail Hussain, Tausif Hussain, and Nurjahan Shodhi, Olga Poshariba, and Deborah Beach, our professor. So thank you for the opportunity to present this work. So in this project, what we discussed, like very often we need to design a device for measuring several quantities. For example, we had a space mission, and we want to send a lot of sensors that measure temperature, radiation level, measure pressure, and if it's landing on Mars, then maybe we need to measure the amount of water. We want to measure the water and so on. Ideally, we should measure each quantity with maximum accuracy, but this is usually not possible since our resources are limited. For example, for space exploration, there is a limit in size, the limit on weight, and the limit of energy consumption. Within this constraint, we can have several options with different accuracy. For example, we have one option, which is we measure distance with accuracy 1 meter, and temperature with accuracy 10 degree. We will describe it by a tuple, for example, 1,10. And another option is which we measure distance with accuracy 2 meter and temperature with accuracy 3 degrees. We will describe it by a tuple, for example, 2, 3. Which option should we select? So, in some cases, we have a precisely known objective. For example, we want to check if there is life on Mars, so we check whether there is water and whether there are organic molecules. So this measurement must be done with the maximum possible accuracy. However, in many other cases, we are just exploring. We don't know what will be the final result. For example, we are building a new system of telescopes sent out to space. We do not know what we will find, but still need to select one of possible options. So which option should we select in such cases? Moving to the next slide. We will formulate our problem in precise terms. So we want to know which is the best way to do that. So what we need to describe is some relation better that will enable us to compare any two options A and B. We will denote like this way: A is better or we'll denote like A is better or of the same quality, or alternatively A is greater than or equal to B. By a greater than or equal sign, we are denoting this.
It's not greater, it's special sign. Greater, better.
Okay, so is it a better or?
Yeah. We'll denote it by this symbol, that's it.
We'll denote this relation by this symbol.
Symbols don't necessarily convey.
So we do know before what this relation will be. So let us describe what are the reasonable properties that this relation must satisfy. First, this relation should be consistent with common sense. If A is better than B and B is better than C, so then A should be better than C. So of course, if in option A all uncertainties are smaller than in option B, then A is better than B. So also we don't know which of the quantities we are more important. So the order in which we list the corresponding accuracies should not affect which option is better. For example, if we decide that the tuple 2, 3 is better than tuple 1, 0, then 2, 3 should be better than 10, 10, 1.
Not 1, 0, 1, 10.
Sorry, it is 1, 10. So, for example, the tuple 2, 3 is better than tuple 1, 10, then 3, 2 should be better than 10, 1. In general, no matter what permutation we apply to both options, it should change which option is better.
It should not change. It should not change.
It should not change which option is better. Such relations are called permutation invariant. Moving to the next slide. In this slide, we will also talk about other option, which is the scale invariance. Finally, the selection should not depend on what measuring units we use for quantity. For example, for measuring length, we can use meters or centimeters. If we switch the measuring units, this should not affect the relation between the accuracies. So what does it mean? We can measure distances using centimeters or meters or inches. So we can measure weight in kilograms, grams or pounds, and the accuracy correspondingly, what is the accuracy of measuring distance? The same accuracy as different numerical values in different units. For example, the accuracy of 1 centimeter is 10 millimeter and 0.01 meters. Our comparison should not depend on which unit we are using. So what does it mean? That means if a tuple with A's is better than the tuples with B's, and we rescale all the values, that is use different units for each quantity, then the rescaled A should still be better than the rescaled B. For example, suppose that the tuple 2, 3 is better than the tuple 1, 10 when we use meters and degrees Celsius. Instead of meters and degrees Celsius, we could use centimeters and degrees Fahrenheit. So we are changing the units, measuring units only. So here 2 meters mean 200 centimeters, and difference of 10 degrees, C means 10 degrees Celsius means a degree of 18 degrees Fahrenheit. So instead of the pair 110 in the new units, the same option is described by the pair 118. Similarly, the pair 2, 3 becomes 205.4. So if choosing a different unit simply means we multiply by a constant. So if instead of meters we use centimeters, it means multiply by 100. If instead of inches we use centimeters, it's multiplied by 2.54. So the result, if we rescale both A and B by lambda, so if the point A1 to AN is better than point B1 to BN, then rescaled point A should be better than rescaled point B. And this is called the scaling variance. Moving to the next slide. So in this slide, we'll talk about our result, formulation, and the meaning.
You don't have to repeat the word. Now we're moving to the next slide. That's not wrong with that. Correct.
So our result is that if we have a permutation invariant and scale invariant relation, then alternative A is better than alternative B. if and only if the product of all A accuracies is smaller than the product of all B accuracies. For example, the alternative 2, 3 is better than the alternative 1, 10 because 2 times 3, which is 6, is smaller than 1 times 10, which is 10. So how can we interpret this method? For example, if we measure distance between 0 and 1 meter with the accuracy of 1 centimeter, then we have 1 meter or 1 centimeter, which is equal to 100 different alternatives. This is 1 meter divided by 1 centimeter equals to 100 different alternatives, which are 0 centimeter, 1 centimeter, 2 centimeter. So in general, if for some quantity we have the range xi, and we measure this quantity with accuracy ai, then we have xi divided by ai, different measurement results. So the overall number of possible resulting tuples is equal to the product of these numbers. So this product is equal to the overall volume x of the set of tuples divided by the product of accuracies. So minimizing the product of accuracies means minimizing the number of possible measurement results. Maximizing the resulting results. So minimizing the product of accuracies means maximizing the number of possible measurement results. So our criteria simply means that we select an instrument that will give us more alternatives and thus more information. Let's talk about the proof. How do we prove our result? If n is equal to 2, then permutation invariance means what? So for any two positive numbers a1 and a2, the pair consisting of the square root of a1 and a2, square root of a1 and the square root of a2, the pair consisting of the square root of a1 and a2 is equivalent to the pair in which these two numbers are swapped. Like here we see root of square root of a2 and the square root of a1. So why? So suppose that the first pair is better than the second pair. That means square root of a1, square root of a2 is better than square root of a2, square root of a2. A permutation swapping the values transforms the first pair into the second one. Thus, if the first pair was better than the second pair, so then due to permutation invariance, we would conclude that the second pair is better, which contradicts to our assumption. Thus, the first pair cannot be better than the second pair. Similarly, the second pair cannot be better than the first pair. So, these two pairs must indeed be equivalent. Now, we apply scaling values with lambda 1 equal to square root of a1 and lambda 2 equal to square root of a2. Here we see the lambda 1 equals to square root of a1 and lambda 2 equals to square root of a2. Then we conclude that the pairs a1, a2 is equivalent to the pair in which both numbers are equal to the square root of the product a1 times a2. So by transitivity, if the two options have the same product a1 times a2, they are equivalent because both pairs are equivalent to the same pair of equal numbers whose product is equal to a1 times a2. So by transitivity, if we have two options with the same product, they are equivalent. For n greater than 2, we can similarly prove that if we replace two values with another two values with the same product, the option remain equivalent. In particular, we can replace the first two elements of a given tuple by a new pair in which the first element is equal to the nth order root s of the product of all n elements. Now we can continue doing this. If we have first k element equal to s, then we replace the next two elements with a new pair whose first element is s and whose product is the same. We continue going like that, smoothing everything. As a result, we get an equivalent tuple in which all the values are the same, nth root of the product of a1 to a. For this new tuple, the product of all these elements is the same as the product of all elements of the original tuple. So each alternative is equivalent to this alternative for which all the values are the same. And if we have all accuracies smaller, the corresponding option is better. So conclusion is that if the product is smaller, corresponding alternative is better. It is important to mention that we did not select any criteria beforehand. We came up very naturally through the scale and permutation invariance to the criteria that the product of uncertainties is better. Intuitively, one may think that some weighted average is a reasonable criteria here, but no, it is not. It is not scale invariant. Thank you all for your attention and your time.
Any questions?
Question for